Okay, you should have out lecture 38 notes, unusual values. Okay, for a normal population of data, any particular value would be considered unlikely because it's a continuous random variable, right? If I draw well, it doesn't have to even be for any normal random variable, so I don't have to put it centered over 0, so it could come along like this and go like this. Any particular value that I pick anywhere is unusual because I kind of think of, well, let's just look at the area right above that particular value. It's infinitesimally thin, right? Right above that value, the area right above it is infinitesimally thin. So any value is really unlikely. But what we want to look at is what we call unusual values. And the next sentence there is, so you can just make a little note, like you could just say something about area right above any value is 0, so any particular value is just unlikely. But what we want to look at is what we call unusual values, and the picture there, of course, is what we mean by unusual is far away from the mean. The mean is where the data or the random variable values are centered, and of course a bigger standard deviation means that it tends to be spread more. The data or the values of the random variable tend to be spread more. There's more probability away, and a smaller standard deviation means that it's clustered in. But whatever the standard deviation is, if we go out far enough, we expect to get values out here that are unusual, right? This might be considered unusually high. And way back over here, this might be unusually low. We don't generally expect to get values that are many standard deviations away from the mean in either direction. So those are actually what we mean by unusual values. And of course, the way we'll think about it is we'll think in terms of tail probabilities. All right, a value way the heck out here is going to have a small tail probability, or way out here will have a small tail probability. Again, by tail probability, I just mean if I'm to the right of the mean, I'm looking at the tail for a particular value being everything that goes beyond it, and so to the greater than it, and the area would be the tail probability. Over here to the left of the mean, the tail would be all the values that go beyond it, so farther left, and the area would be what I call the tail probability out there. All right, so let me be a little bit more precise. So in that next paragraph, I just kind of explained that a little bit, but for an unusual value, what we'll mean is that it's a value, as I said, far enough from the mean such that the tail probability will be small. And what do we mean by small? Well, we've used 5% in the past, but now we're going to get to where we'll define it in context, what we mean. So, for instance, we'll give a cutoff probability, and the symbol that's usually used for the cutoff tail probability is alpha. You can read there. So alpha is the small cutoff tail probability that cuts it off between probabilities, tail probabilities that indicate not unusual, usual values versus unusual values. So, for example, what we'll have is if we think in the think z-scores here. Think z-scores, and we have our cutoff tail probability is alpha. So what that means is, doesn't look very symmetric, does it? What that means is that if I go out here a certain distance, if this probability, this area, is alpha, then anything out here is unusual. Unusually large. All such values out there, right? And if I come way over here, stretch it out a little bit more, and I'm going to try to get about even so that my value alpha is in this tail. What I would then be saying is I'd be saying anything out here would be unusually small. You can barely read what I'm writing. Unusually small, right? Those values. Okay, values inside would not be unusual. All right, and in fact, What is the z-score? That's the cutoff. We have a symbol for that. The z-score that has alpha area to its right, we call z sub alpha. And over here, this would be negative z sub alpha, right? Because if you just fold it over, you get the same area here as over there, so the same z-score over here is there, except it's negative. And I can say I'm off a little, it's because I'm not perfectly symmetric, but you get the idea. Okay, so I can think in the following way, and we're going to do this over and over. When I talk about an unusual value, I could compare its tail probability with alpha. If its tail probability is smaller than alpha, that means it had to be farther out, so it has less tail probability here or over here. So I'd conclude it to be an unusual value. If its tail probability were larger than alpha, that means it's closer in because it has more tail probability than alpha, either this way or this way, so it's not going to be unusual. Likewise, I can just look at its z-score. Is its z-score farther away from the mean than this critical value of z sub alpha to the right or negative z sub alpha to the left? So I can compare z-scores or I can compare tail probabilities to decide if something is unusual or not based on our criterion, whatever we've chosen for the cutoff probability for unusualness. Okay, let's do a couple examples then. Let's do, I guess let me change my color here. Example. It says here, suppose the hamburgers at Moo-rific Steakhouse have a mean of 6 ounces and a standard deviation of 1/4 of an ounce, 0.25 ounces, uncooked. Let's let the cutoff tail probability for unusualness be alpha equal 1%, which is just 0.01, right? Okay, question. If we consider a sample of uncooked burgers of size n equal 100, suppose we take the mean of that, and the mean is 6.06 ounces, would that indicate an unusually large amount of meat? And of course, because the 6.06 is bigger than the mean, I'm thinking of it being over to the right, so I'm asking if it's unusually large. I wouldn't be asking if it's unusually small. It's obviously bigger than the mean, right? Okay, so let's notice that let B equal weight of meat in randomly chosen burger. All right, the burgers themselves may not be normally distributed. We aren't told that, but we're told the mean is 6 ounces. We'll assume that's 6.00, and the standard deviation is 0.25. So B bar, so look, n is 100, it's greater than or equal to 30, so we can go, we can do this. We can say B bar is normally distributed with the same mean, I put in the hundredths position, 6.00, comma, what's the standard deviation? It's 0.25 divided by the square root of 100, right? So we get 6.00, comma, and that will be 0.025. All right, there is B bar. And the question is, we are told that, okay, we're told that we have a mean of 6.06. And the question is that unusually large amount of meat? Well, let's compute the probability. I guess I'm going to do this one way first. We'll go, let's compute the probability that B bar is bigger than or equal to 6.06. I'll find the tail probability associated with this value, all right? And this is well within your ability to do. I'm not going to do the details. We will get you will get 0.064. You should get. There's a mistake, of course, if you do it very carefully. You will not get 0.064. You will get 0.0082. The rest of the problem is worked correctly, but just know that that number right here, 0.064, should be 0.0082. That, all right? And so what does that tell us? The tail probability here is less than the cutoff probability of 1%, which is 0.01.
Okay, now that's obviously ridiculous because 0.064 is bigger than 0.01. I just knew what the correct answer was, but I'm writing down this incorrect number here and not even thinking that it's bigger than 0.01. The correct answer again is 0.0082, which is less than 0.01. 0.01 is bigger than what this probably should be here, 0.0082.
That tells me it's unusually large. Here's the picture. Here's the picture. If I convert to, if I've converted to, let's see, well, I can draw the picture, or if I am in terms of z-scores, I'm going to go ahead and draw it as a, do I want to do that, or let's see, what should I do here? I think I will draw it, not with z-scores, but I'll draw it using just thinking of the normal curve for B bar. All right, so what we have found is that way out here at 6.06, I have an area of 0.064, right? A tail probability of 0.064, and that's less than 1%, all right?
Obviously it isn't again, but it should be 0.0082, which is less than 1%, and that's what we need. I knew what the right answer was, I'm just writing that number down wrong, so I apologize for that.
The 1% tail would correspond to, we'll see this in a minute, it would correspond to a value back here somewhere, right? There's some place back here where I would get a 1% area to the right. And since this is less than this, we conclude that we have an unusually large amount because our cutoff tail probability was 0.01, sorry, I have 0.064, I think it's 0.0064. Please, yeah, sorry, it's 0.0064.
Well, I fixed it a little bit, but it's actually 0.0081. Okay, and that is still less than 1%, so everything works through. I just still have the wrong number there, 0.0064. It's supposed to be 0.0081, all right? But you should be able to get that on your own, excuse me, and you should see that it all works out, all right?
That's what makes it less than, all right? Yeah, there's two zeros there, so it is less than 1%. It's less than 0.01. Sorry about that. Okay, but anyway, so my tail probability is less than 1%. So this is an unusually large amount of meat. Now remember, we're doing a sample mean of 100, right? 6.06, that's 6 6/100ths of an ounce extra over a mean. That doesn't seem like much, right? And for a single burger, it probably isn't much. But this is a sample of size 100, and the mean is 6/100ths of an ounce over. And for our cutoff probability, we have a large amount, too large. All right, let's see. The other way to do this, let me do it the other way. Other way, compare z-scores. All right, our z-score for the meat was 6.06. You should have found this when you worked this through. It has a z-score of, you would get it to be 2.4. All right, and you should have gotten that when you worked through this right here. And our cutoff z-score is z sub 0.01, right? And that it works out to be, I have it here, 2.33. So what's the picture there? The picture there is, we have the z random variable, and boy, is that not symmetric. A little better. Okay, this is z. What we have here is our cutoff And remember what I said? Anything outside here is unusual, right? So we have 2.4 right out here. So it's unusual because it's out there in the tail. This tail corresponds to, this tail right here corresponds to that tail. The tail starting at z.01, where I get actually 1% area to the right, corresponds to, I didn't figure it out, but it's some value here that's going to be to the left, right? So either way you look at it, the value we've chosen is more extreme than our criterion allows for it to remain usual, so it becomes unusually large. All right, let's do the next example. So you read that while I rub out a little bit. We're looking at bags of marshmallows, and the mean number of marshmallows per bag is 40, and the standard deviation is 2.1. All right, so we take a sample of size 49, and notice I always pick numbers that are easy to square root. In the real world, your sample size probably won't be easy to square root by hand, but that's okay because a calculator or a computer will do that with no problem. But this sample is a sample of size 49, and it's discovered that in that sample, there's a mean of 39.5 marshmallows per bag. The question is that an unusually low number of marshmallows? And of course, to answer that question, we have to have a criterion for what we mean by unusually low. And this thing really rattles when you rub hard on it. And the criterion we have is alpha is 2.5%. So this is, next example, I'm not going to write that all out, but I'm going to say that M equals number of marshmallows from a randomly chosen bag. Okay, and we are told, aren't we, that we aren't told that it's normal. We just know that the mean is 40 and the standard deviation is 2.1, but we're told that n is 49, which is bigger than or equal to 30. So the mean, sample mean, will be normal with mean equal to what they say there for a bag, which is 40, and what they get for the standard deviation is 2.1, but I divide by the square root of the sample size, so what I get is normally distributed with mean 40, standard deviation 0.3. Okay, the question is a mean of 39.5 marshmallows per bag, is that unusually low? Well, alpha is 2.5%, which is 0.025. So the question is my probability that the mean is 39.5 or below, how does that compare with this probability, this cutoff probability? And again, I may make a point here of asking, I think, how do we know, are we looking for unusually low or unusually high? Well, if we're starting with a value of 39.5, that's below the mean, so we're not going to ask is it unusually high. The question is it unusually low? So we're way over to the left now. Are we so far to the left that we say it's unusually low? Let's figure out. Here's my cutoff probability. So let's check the probability. And please, again, always stop and try to work through. If you get confused and you have to watch a little, but try not to watch it all the way through the first time, right? Try to get it the first time. Probability M bar less than or equal to 39.5. So the picture is... So I'm here, here's the mean 40, so I'm here at 39.5, and what I want to know is I want to know about this probability, right? And the question is that probability smaller than that? If it is, that means I'm out so far that it's unusual. If it's not smaller than that, then I won't say that I'm unusually low. So we compute this, and I will leave you to do it. And again, you should have no problem with that. And what you end up with is 0.0475. You have to convert to z-scores and do all that, of course, but you end up with 0.0475. That's greater than 0.025. So the value that's going to have 0.025 is out here somewhere, so it's not unusual. This value that I have is not unusual. So, not unusually low, right? And I want to do it looking at z-scores. So go below, and there's another space. And using z-scores, here's what we have. We have a critical value of, I have a area here of 0.025. So the critical value, I'm going to call that CV for critical value, that'll be negative, won't it? Z.025. And if you look up Z.025, you get 1.96. So this is negative 1.96. And what is the z-score of, what's the z-score of 39.5? You had to figure that out to get down to here, and that turns out to be negative 1.67. So that puts it about right there, right? That's negative 1.67. That's the z-score of 39.5 marshmallows per bag. So it's not unusually low. We can see that either way. So not an unusually low value for the sample mean. Okay, so once again, the probability, the tail probability for this sample mean was bigger than our cutoff tail probability for unusualness. It has to be smaller before we say it's unusual. So I can see right there, it's not unusually low. Over here, I can do it in terms of z-scores. The z-score that corresponds to the cutoff probability is out here, and the z-score we got for the 39.5 is not out that far. It's in closer to the mean, so it is not unusually low. All right.